Greetings, Unitarians! It's your boy, Griswold, and today we're going to talk about reconstructing normals after applying a vertex offset using a displacement map. Using a vertex shader, we can apply an arbitrary offset to the vertices of our geometry using a bitmap as a displacement texture. Now, what if we want to apply lighting to these surfaces? I've written a shader that gives us this reflective pearlescent surface, as this effect will be most pronounced with shiny materials. If I increase the amount of displacement applied to our surface, we'll see that the vertices are still being offset, but the light is still interacting with our surfaces based on their original normal direction. This is most pronounced in the case of our plane, where we'll see that even though this displacement has been applied, it's still being shaded as if it were a flat surface. We can apply a technique called the partial derivative to calculate new normal directions for this surface based on the offset vertices. The effect is subtle, but it adds important information about the shape of our surface. So let's write a simple displacement shader to start. I've done a few things to set up our scene. I've set the shading mode to shaded wireframe because right now we're really only concerned with the vertex position from our shader. I've added this high poly sphere and a high poly plane to preview our material on. And I've connected some sliders for the specular and gloss properties because this effect will be most pronounced on a shiny surface. Now, to start, we'll add a texture 2D node that will house the displacement map we're using to offset our geometry. We'll call that height, and pipe that into the vertex offset inlet on our main node. And already we'll get some displacement, because before we started, I specified this Perlin noise height map. If I set that back to none, we'll see that the plane is still being displaced, and that's because by default the texture 2D node will be white. We'll want to set that to black. And if we bring back our Perlin noise texture, we can add another property that will specify the magnitude of this displacement. So we'll drop in a value node, call that strength, make it default to 1, and multiply that by our displacement map texture. If we rig that to the vertex offset, we'll have a new property in the material inspector that lets us control the strength of the displacement. We'll notice, however, that this displacement is being applied on a diagonal axis, and that's because as we're using a grayscale texture, the displacement will be applied on the X, Y, and Z axes uniformly. We want to apply this offset in the same direction as the normal of our surface. We can do that by dropping in a normal direction node and adding that to this multiply operation. And we'll see now that the vertices expand in the direction that the surface is facing. Now, if we turn off the shaded wireframe and go back to shaded, we'll see the problem we described earlier, which is that even though our vertices are being displaced, light is still interacting with the surface based on the original normal directions. So in the case of our plane, it'll be shaded as though it were flat, even though this displacement has been applied. Now, before we go about implementing our partial derivation, let's explore this concept in abstract. If we look at our plane from the side, we'll get a two-dimensional line. These blue arrows indicate the original normal directions of the surface, which, as we know, are pointing up. Now, if we imagine applying displacement to this line, we'll get a curve. However, we'll see that just as in our shader, the normal directions are still facing up. We want our normal directions to be perpendicular to the surface like this, so the light can interact with the surface correctly. In order to do that, let's consider a single point in isolation. Its normal direction is pointing up, as where we want it to point perpendicular to the surface, so what we can do is draw a line from this point to a neighboring point, and draw a normal direction that's perpendicular to this new line. Now, as the distance to this neighboring point becomes smaller, this new computed normal direction will become more and more accurate. We can repeat this process for every point on our surface in order to calculate the correct normal directions. Now, since we've been considering our plane as a two-dimensional line, In order to complete this process in 3 dimensions, we'll have to sample 2 neighboring points instead of 1. So, in order to sample our displacement texture at 2 neighboring points, we'll use something called a texture asset node, which allows us to create one field in the material inspector for a texture and then reuse that texture multiple times. We'll delete our original height texture property, call this displacement, and create 3 more textured 2D nodes. If we pass this text output of our texture asset node into the text inlet of these texture 2D nodes, you'll notice they turn gray, indicating that they're no longer fields exposed in the material inspector. They're simply duplicates of the texture field we've defined here. Now, this bottom texture node will serve as the original point on our curve. This is the amount of displacement we're actually applying to our surface at this point. Let's make this default to our Perlin noise again, and pass the R channel into this multiply node. In the material inspector, we'll need to specify our new displacement texture, again the Perlin noise, and we have the same displacement shader as before. The next thing we need to do is sample this displacement texture at 2 neighboring points. We can create a new property called PD distance check, set its maximum to something small and its default to something even smaller, and what this number represents is the distance to our neighboring point. Now remember that as this distance becomes smaller, we get a more accurate normal direction, and that's why this is defined in such a small range. So, we'll need to construct 2 new UV points from which to sample our texture that are offset on the X and Y axis correspondingly. We'll use 2 append nodes to create 2 UV offsets that apply this PD distance in 2 dimensions. We'll connect it to the R or X input of this append node and the G input of the second, and we'll connect a constant value of 0 to the G and R node of these append nodes. Next, we'll subtract these offsets from our original UV coordinate. Now, you'll remember from earlier videos on Shader Forge that the Texture 2D node uses the UV coordinates baked into the geometry by default. So, passing the output of this node to the UV input of this texture node will be a redundant operation, but we'll include it for clarity's sake. Next, we'll use 2 subtract nodes, pass our UV coordinate into the A inlet of each, and subtract our X and Y offsets accordingly. And we'll use these 2 new UV coordinates as the inputs for these 2
as the
normal
sample
inlet expects a 3-dimensional vector. Next, we'll construct a vector that combines the value from these new sample points into a single 2D vector. We'll remember that this is the texture as offset in the X direction, so we'll pass that into the R or X value of the append node, and pass the R into the G value of the append node, and we're using R as this is a grayscale image, and each of these outlets will return the same value. Next, we'll subtract the value of the original sample point of the displacement texture from this new combined offset vector. Now, if we bring our PD distance check variable over and start to slide this around, you'll notice that we're getting something that starts to resemble a normal map. If we put our PD distance check back and try to pass this into the normal direction for our main node, we'll notice that it's disabled. So we'll notice that this image only has an RNG component, so we need to add a B component to the normal direction in order to pass it into the normal inlet. We want our normal directions to have a total magnitude of 1, so in essence, what we need to do is calculate the amount of remaining space in this offset vector in which to add a Z component to this normal direction. First, we need to get the square magnitude of this offset vector. We can do that in shorthand by using a dot product and passing our offset vector into both inlets. Now, the dot product has a special property whereby applying the dot product to the same vector twice will give us the squared magnitude of that vector. We'll need to subtract that from 1 to calculate the remaining space in our vector, and then square root that value as we were operating with the squared magnitude before. Finally, we can use an append node to combine our xy offset with this new z value that we've computed. Let's bring our PD distance check slider back again, and if we slide this value around, we'll start to see some pink clouds that might remind us of a normal map. Let's pass that into the normal inlet of our main node and see what we get. And voila! You can see that the light is reacting to our surface using the new normal directions that we've computed using the partial derivative. Let's move our light direction around a bit, and we'll get these nice specular highlights. Now we need to do one more thing before we're done here. Let's set the strength of our displacement back to 0, and we'll see that the normal directions are still behaving as though the surface was displaced. What we need to do is multiply this new offset vector that we're computing by the strength of our displacement. Further, since this value can't exceed a magnitude of 1, we'll want to clamp it using a clamp simple node from a minimum range of -1 to 1. We'll multiply our offset vector by our displacement strength, pass that into clamp, and then replace the output of this subtract inlet with the output of our new clamp node. Now we can see that the strength of these new computed normals will grow and shrink as the magnitude of the displacement changes. That about does it for today's tutorial on the partial derivative. For now, I'll leave you with this shiny, wavy displacement texture and bid you adieu. Thanks for watching, and keep on shading.